constant matrix, and then from there applied the strain energy approach to obtain this expression for beam stiffness. So now we just have a little bit left to do to complete this process. So we're going to define the work that's done in a virtual displacement of the beam. In order to do that, right, we're going back to this generic representation of a beam element that is experiencing force and moment at each end, and they're shown in the positive direction. So a couple pages back, we looked at this in terms of the deflections, right, or deformations, which are the transverse and rotation of each node. And I did sketch on here the corresponding force and moment directions that would cause that. So now we're going to focus on those forces. All right, and we have our positive sign convention noted here. So, all right, positive moment counterclockwise corresponds to positive counterclockwise rotation, and positive upward force corresponds to positive upward displacement. So this is a 2 degree of freedom system. If you're not familiar with that expression, degree of freedom is essentially defined as a way that a node can move that is tied to deformation of the structure. So since this element, right, that we're considering a beam in bending, the relevant displacements are transverse, all right, so that's 1 degree of freedom, and rotation, that's the 2nd degree of freedom. So at each node, you have 2 different ways that the node can move. All right, and that's transverse rotation or transverse deflection and rotation. So each displacement, or each way that the node can move, is associated, of course, with the corresponding force. So transverse displacement is associated with a transverse force, and rotation is associated with moment. We'll come back to that concept later on. Now, under a virtual displacement of these generalized deflections, right, which are rotation and displacement, we have a virtual work expression now, and again, we're holding the forces constant. So the increment in work done due to virtual displacements is going to essentially just be the force times the associated virtual displacement. So F1 would be multiplied by lowercase delta V1 plus M1 multiplied by lowercase delta theta 1 plus F2 times lowercase delta V2 and M2 times lowercase delta theta 2. All right, or in matrix form, we can write this as lowercase delta delta transposed times the generalized force matrix. And now imposing the requirement for equilibrium, right, the increment in potential energy is the increment in internal strain energy minus the increment in work done. And this is all due to virtual displacement, right, which is, again, an imaginary displacement, so not real. There's no increment or no additional force associated with that virtual displacement, since we held the forces constant, right? So we'll have our delta delta transpose times, in parentheses, the stiffness matrix K times our generalized displacement matrix minus the generalized force matrix. Set that equal to 0 for equilibrium. And since the delta-delta product, or if you can think of it as a product, really the lowercase delta isn't a value, it just represents the variation in displacement. But it's a non-zero value. For variation in deflections. Okay, so the variation is represented by the lowercase delta, and the generalized deflections are represented by the capital delta. We can say then that the stiffness matrix times the generalized displacement matrix is equal to F, the generalized force matrix, being the condition of equilibrium. So then on the next page, we have the expanded form of that same matrix, right, with the 4x4 representing stiffness matrix K, and then you have the generalized displacements equal to the generalized forces. You'll notice in this form that the generalized displacement matrix has mixed units in it, right? Because we have displacements in units of length and then rotations, which are dimensionless. And then also in the generalized force matrix, we have mixed units, right? Force and moment. So we want to make some modifications to simplify our application when we solve these problems by hand in particular. So in order to do that, we will multiply our rotations by the length of the element. And in doing that, right, because remember the first column in this matrix gets multiplied by, or the second column gets multiplied by theta 1L, the fourth column gets multiplied by theta 2L. So if we multiply those rotations by L in this matrix, that means we are essentially removing it from the columns that are associated with that value. So we've just eliminated one L term from columns 2 and 4. And then the remaining L terms exist in rows 2 and 4. So that will correspond to our moment rows. So if we divide our moments in the generalized force matrix by the length, now we have made those units consistent in both the delta and F matrices. And dividing those moment values by L, we also need to divide the other side of the equation by L, which will eliminate the remaining L terms in our stiffness matrix. So now not only do we have consistent units in delta and F, but we have a 4x4 stiffness matrix that's only numbers, right? So we don't have to worry about that L term within that matrix. So that is really convenient for hand calculations and solutions. when you get into numerical solutions or, writing a computer program, it doesn't really make a difference if you do this step or not, as long as you treat the problem appropriately. But this comes in handy when we solve these problems by hand. So now what we have is a set of 4 equations that relate beam end deflections to the generalized corresponding beam end forces. And in our nice new numerical matrix form, we now have same units in delta and F. First column, right, is multiplied by V1, second column by theta 1L. Third column is multiplied by V2, and fourth column is associated with theta 2L. I always like to label the columns of these matrices according to the displacements that they're associated with, just as a reminder that that's what they're going to be multiplied by. You don't have to do that, but that's what I like to do. And then note that this matrix is symmetric about the main diagonal, so that will always be the case. Oops. All right, so then going back to the 2 degree of freedom concept, all right, since this is 2 degrees of freedom, that means that at each node of our problem, we will know exactly 2 values going into the problem. And that's going to be the displacement or the force and the rotation or the moment. Any questions so far? Okay. So next we'll start an example. This is a very simple example, right? A simply supported beam with an applied moment at the right end. So this is a positive moment according to our sign convention, right? Which is always positive counterclockwise no matter where you are. So remember that it doesn't matter if you're on the left end of a beam or the right end of a beam, right? That would be interpreted maybe differently for mechanics sign convention, but counterclockwise will always be the positive direction for moment and rotation within the finite element solution. So to start, we want to identify what we know at each node, right? So just continuing on from that last thought, we know exactly 2 things at each node. So at node 1, we know that V1 is equal to 0 because it's a pin support. So that means we don't know, or I'll say, but because it's a pin support, right, we don't know the rotation. So theta 1L is an unknown. since we know that V1 is 0, we don't know the reaction force, F1. And we don't know the rotation. That means we do know that the applied moment at M1, since there isn't one, is equal to 0. At node 2, similarly, we know that V2 is 0, since it's a roller support. That means we do not know the corresponding force. And we don't know the rotation. But we do know the moment. And I'll just, to be complete, I'll add our positive up for the sign convention of displacement and force. All right, so now to begin the solution, we are going to essentially just start with this equation right here. All right, so I'm going to make a note here that this is your starting point. For a given beam element. So if you want, you can just copy and paste that here. I'm going to go ahead and rewrite it. So we have EI over L cubed out front. And then first column is 12, 6, negative 12, 6. Second column, scoot that down a little. Second column is 6, 4, negative 6, 2. Third column, negative 12, negative 6, 12, negative 6. And fourth column is 6, 2, negative 6, and 4. This will be multiplied by V1, which we have just identified as being equal to 0. Theta 1L. V2, which we know is 0 in this problem. And theta 2L. And we'll set that equal to forces. So we have F1, M1 over L, F2, and M2 over L. And so our M1 over L is 0, M2 over L is going to be positive M naught over L. All right, so a couple of rules that apply to all these types of problems. First, either the displacement or the force must be specified, never both and never neither. That's just kind of a long-winded way of saying what we said up here, right? At each node, you know exactly two values, right? Either displacement or force and either rotation or moment. So we can visually see that, right, between these two force and displacement matrices. In each row, we know one or the other, not both and not neither. Second rule is the first partition will be the matrix of rows for which loads are known. And I'm actually going to amend that to say forces. It is loads, but I guess it's fine to leave it as loads. All right, so we'll rewrite then, take those rows with known forces. So that would be your rows 2 and 4 in this case, because we know the moments there. So that's going to be, all right, taking rows 2 and 4. And I'm just going to rewrite the whole thing. So we have 6, 6, 4, 2, -6, -6, 2, 4, times 0, theta 1L, 0, theta 2L is equal to F1 and 0. Now, since V1 and V2 are 0, right? That means we really don't need the first and third columns here, because those columns are just going to be multiplied by 0. So they're not helpful for our solution. So you can do that elimination up here, right? And then you don't have to write all 4 columns in your first partition. So the first partition then simplifies to 4, 2, 2, 4 for the stiffness matrix times theta 1L and theta 2L is equal to, let's see, what did I messed something up above. Yeah, I don't know how I got that wrong. All right, so in the force matrix, all right, we're taking the second row on the fourth row. So it's 0 and m naught over L. So this is your first partition equation, which we will use to solve for the unknown displacements. So there's a K times delta is equal to F. So we just need to take the inverse of that stiffness matrix and pre-multiply both sides. In order to solve for the displacements. And you may recall that for a 2 by 2 matrix, the inverse is really easy to figure out by hand or just in your head. So if you have a matrix with values A, B, C, D, the inverse is 1 over the determinant, which is just the difference between the cross products, times you swap the position of the diagonals and change the sign of the off diagonals. So it would be D, -C, -B, and A. And then the determinant would be AD minus BC. So applying that to this example, we have our deltas being theta 1L and theta 2L will be equal to L cubed over 12 EI times 4, negative 2, negative 2, 4, times 0 and m naught over L, which will come out to be L cubed over 12EI times negative 2 and negative 4 times m naught over L. So we could, of course, simplify that further, which we'll do on the next page. Or actually, I'll just continue it here. Right. What do we have? Is that a blank page? Do you all have a blank page on the next sheet? In your notes?
Yep.
You do? All right, let me see. Huh. All right, well, it's not supposed to be blank. That's all right. We'll work with it. So I'm still going to continue this thought here. So this is just, all right, calculating this out. Well, I'll simplify it since we're going to use it again. All right, so that's going to be m naught L squared over 6EI times negative 1 and 2. So theta 1, if we factor the L's back in to the other side, we'd have negative m naught L over 6EI for a dimensionless result. And theta 2 will be m naught L over 3EI. So then that brings me to a third rule, which says the second partition is what is left of the original matrix. So whatever rows have unknown forces in them.
Should that be a negative 4?
One of these, or hold on, you are looking at, I see what you're looking at.
It should be a minus 2 and positive.
1 second, there we go. Here,
Yeah.
let's see. All right, yeah, I didn't miss anything in there, right? Yeah, I think you're correct on that. Yeah, that's correct. So thank you. That should be a positive 4 right there. Good catch. All right, so then going back to the original matrix, we have 2 rows that had unknown forces associated with them. So that was rows 1 and 3. So now we'll just go back and grab those rows. We can forget about the first and third columns since they're still going to just be multiplied by zeros. So we'll just use column 2 and 4 and rows 1 and 3. So that's going to be EI over L cubed times 6, negative 6, second row or second column also 6, negative 6. And then that's going to be multiplied by theta 1L and theta 2L. set that equal to F1 and F2. So here we will plug in the results from the first partition. And this equation is the second partition. So the second partition will always give you the unknown forces. So completing this process, all right, we would have, I'm gonna go ahead and say solving, we get F1 and F2 is equal to m naught over 6L times 6 and negative 6. All right, so I want to point out too, when you're plugging in the results from the first partition, make sure that you're plugging in the theta 1 times L and theta 2 times L values, right? So don't plug these values in, plug this in. So I'm going to say, I'm just going to copy this, put it here so it'll show up, and say, all right, that's what goes in there. All right, so then we have F1 is m naught over L, F2 is negative m naught over L. We want to verify that with equilibrium. So I'm going to just sketch our beam here. Let's see if that'll give me a, there we go, nice rectangle. So we found positive m naught over L at node 1 and negative m naught over L at node 2. Interpreting that to our free body diagram, we can see just visually, yes, sum of forces in Y checks out. All right, sum of moments about any point, all right, I'm going to choose node 2. For this one, it's not quite as obvious to the naked eye, so I'm going to go ahead and write out the whole equation. We have negative m naught over L times the length L plus, I forgot to include our applied moment, right? M naught is equal to 0. So that does check out. All right, length L. And now that we've established equilibrium is satisfied, let's go ahead and sketch the deflected shape based on the values we found for nodal rotations at 1 and 2. So we found theta 1 to be negative m naught L over 6 EI, and theta 2 m naught L over 3 EI. So we found that theta 2 is twice the magnitude of theta 1. All right, so gut check, that makes sense since node 2 is where the moment is applied. And also, the rotations at the two nodes are in opposite directions, which also makes sense given the configuration of the beam, right? So a negative rotation at node 1 would be a clockwise rotation, and a positive rotation at node 2 would be a counterclockwise rotation. Oh wait, what did I say? Yeah, that's correct. Counterclockwise rotation at node 2. So deflected shape would look something like this. All right, with greater rotation at node 2 compared to node 1. So now we can use those values, right? The theta 1 and theta 2 values that we found, and plug them into that generalized expression for deflection that we derived previously, right? Remember that it was a long v of x, right? So this is the deflection equation from previous lecture. I'm not going to copy the whole thing here, but there's an expression times v1 plus some expression times theta 1L plus some expression times v2 plus some expression times theta 2L. I can flash back and show it to you in a minute, but just to save us all the trouble, I won't write it. For this particular problem, V1 and V2 are 0, so that eliminates those two terms. And then we just plug in what we now know to be theta 1L and theta 2L. And I will write the complete result for you, so you can verify this on your own, but it should be pretty straightforward from the general expression. That should turn out to be m naught times L squared over 6EI times, in parentheses, x cubed over L cubed minus x over L. Yeah, question?
Can you explain how you're doing the matrix simplification to like F1 is just equal to m naught over 6L?
Up here.
Can you explain that?
Sure. So from this equation, if you plug this in for theta 1L and theta 2L, and then just multiply it through, that's the result. This is the result of K times this. I think I might have brought, let's see, so there's a 6.
So should it be negative 6 then over negative 6? If it's negative 1 and I don't know.
So it'll be, all right, 6 times negative 1 plus 6 times 2, which would give us a positive 6.
Right.
And then negative 6 times negative 1
Okay.
minus 6 times 2. Or minus, wait, what?
Right, negative 1.
Yeah,
There.
yeah.
And then also, could this be solved if it was pinned on both sides this way?
Yes, it can.
What would it actually have changed? What would change?
Nothing. Yeah, if it's pin instead of pin roller, yeah, nothing would change in the solution because we're not concerned with axial displacements in the beam problems.
But if it was pinned, wouldn't the angle be the same on both sides?
No, it still would not be the same on both sides. So, trying to think of how best to explain this.
Oh, because there's no actual applied moment on both sides. It's just a singular applied moment.
Yes,
Okay.
yes.
Yep.
Is our matrix for K, where do those numbers come from? Are they always that for like every beam?
Yeah, that'll be the same for every beam element.
Okay.
And that comes from, so the way we derived it in this class, right, it came from the general strain energy and virtual work application, right, where we just started with this general polynomial assumption of a deflected shape. Since we know it's going to look something like this, that fits a polynomial curve.
Right.
And so then applying the boundary conditions, solving for those constants, right, we got here, and then that gave us that general expression for deflection. So this is the equation I was just referring to at the bottom of that previous page, right? And then from there, we went on and applied the strain energy definition to get this long matrix multiplication within an integral, which results in this stiffness matrix. And so that's one way to get there. Another way to get there, which is often taught in structures classes, is to relate the beam deflections or rotations to an imposed force or moment. First starting with a fixed beam, or a beam element that is fixed on one end and free on the other, applying a positive force and a positive moment, and then determining from mechanics what's the transverse displacement and what's the rotation. And then switching sides, so fixing the other end of the beam and looking at the now free end, doing the same thing. You'll end up with the same result by relating it that way. So,
Gotcha.
yeah.
Okay.
But yeah, it's always going to be the same matrix equation, stiffness equation for a beam element. It's going to look different when we look at axial force systems. So we'll do that in the context of trusses in this class. And then, actually, no, do we? I forget. I'm teaching this topic in my structures class right now too, and we are doing trusses this week, so I might get a little bit flipped up as to what I've talked about in which class. But in this class, actually, we're not going to deal with trusses. So that's good news for you guys. We're just going to be doing beams, and then we'll look at frames. So when we get to frames, we'll have to incorporate axial behavior as well. And so then it would make a difference in that case if it was pinned on both ends. Yeah. Yeah. All right, so we're almost out of time here. Let's see where we are. All right, so we just finished that example. So the next example is just demonstrating how if the beam is indeterminate, the solution becomes even easier. The reason for this is because the more indeterminate a beam or structure is, the more known displacements you have, right? So the fewer unknown displacements you have to solve for in that first partition, meaning that first partition matrix gets smaller, it's easier to invert and solve, etc. So this example here, right, starting with what we know, displacement at node 1 is 0. Also, rotation at node 1 is 0. At node 2, displacement is 0, but we don't know the rotation because it's a roller. So applying our boundary conditions, All right. We have 3 known displacements and 1 known force. So the moment at node 2 would be m naught over L. With 3 known displacements, right, first 3 columns are going to get multiplied by 0. We can eliminate those from our analysis. So that just leaves us with 1 column to deal with. So first partition is really easy. Right? We just use that row with the known force, so that's the 4th row, and we only have the 4th column to think about. So it's really not even a matrix equation anymore. All right, then the second equation, or well, I guess I'll write the result here. So theta 2L, we get m naught L squared over 4EI. So then the second partition, we have to go back and use the remaining 3 rows. We're still only using that 4th column though, right? So that's a common mistake that I see a lot of students make when first using this method. It's tempting to want to use the same, the 3 columns that you didn't use before, but just remember we're never using those columns once we've eliminated them from our matrix equation. So we have the 3 rows of column 4, 6, 2, negative 6. Multiply that by theta 2L. Set that equal to the reaction forces. All right, so here we are going to be plugging in that for theta 2L. And so the result will be 3 m naught over 2L for F1, m naught over 2L for M1 over L, and negative 3 m naught over 2L for F2. And then from there, you can draw the free body diagram, verify equilibrium, draw your deflected shape, write the expression for deflection, draw the shear and moment diagrams if you want, right? All kinds of things. So I'll wrap that up next time, and then we'll have a few more comments on boundary conditions, and then roll right into adding more elements to our problem. So we'll look at beams with multiple elements. So, all right. Any questions? All right, all good? Well, thank you all. See you Friday.
Actually, Dr.